Hello everyone, I'm Harriet Linda from SRM Institute of Science and Technology. In the previous lecture, we studied the basic concept of backtracking and an application Enquiries problem. So in this video, we are just going to see the concept of sum of subset problem and Hamiltonian circuit problem using backtracking technique. So I think all of you know about the basic concept of backtracking. We are just going to start from an initial solution when we are just going to explore. So this is normally represented by means of state space tree. State space tree, it is having two different nodes. One is the promising node, another one is the non-promising node. Promising node that has the potential to lead to a valid or a optimal solution. But non-promising node is nothing but node that cannot able to lead to a valid or an optimal solution. So that is the basic concept what you are just studying in the backtracking. If you are just attaining an invalid solution, we are just going to the previous step. That is, we are just going to backtrack to the previous step and we are just going to explore the solution. So in this video, we are just going to see about one concept that is called as the sum of subset problem. So we are just having a subset. So normally we are just having a set that is A1 to AN. So all the numbers, it is nothing but it is an n positive integers only. And we are just giving a target. So what is the basic concept we are just going to include in the sum of subset problem is we are just going to create a subset. The subset sum that is equal to a positive integer that is normally called as D. So one such example I am just saying here. So one array set I am just taking here, that is 1, 2, 5, 6 and 8. The target I am just giving here is D equal to 9. I'm just going to create a subset. So one subset I'm just generating is 1, comma, 2, comma, 5. So what is the sum of this particular subset is? That is nothing but it is equal to 8 only. 1 plus 2 plus 5, that is nothing but it is equal to 8. So but 8, that is not equal to 9. So this is not a particular subset. That the main concept is the addition should be that the sum of all the elements in the particular subset that should be equal to D. So what is the D here? It is given here is 9. So here we are having two basic solution here, 1, 2 and 6. So what is the sum of this one? 1 plus 2 plus 6, that is equal to 9. And another one subset that is normally equal to 1 and 8. That is 1 plus 8, that is equal to 9. So what is the basic concept what I am just going to use here in the sum of subset problem is I am just going to use a backtracking technique. So how this algorithm works is, so normally I am just going to sort all the elements in the ascending order. That is given here is A1 that is should be less than or equal to A2, which is less than or equal to AN. I'm just going to sort all the numbers which is in the particular ascending order. After doing this one, I'm just going to create a root node. Root node, the level of the root node that is given as 0. So normally it is having two children. One is the left child, another one is the right child. So what is the basic concept here is, first one is the inclusion of the particular first element. What is the first element? That is A1. That is with A1. So here, what is the weight here is 0. 0 plus A1, that is going to the next level. And on the right side, I'm just going to include here is without A1. I'm not going to, that is exclude the element A1. So that is going to the next element. So 0 excluding this one, that is normally contains the weight that is equal to 0 only. So here normally a particular state space tree from a root node, that is from the starting point, we are having two children. One is the left child, another one is the right child. Left child is nothing but it is the inclusion of a particular element, and the right child is nothing but it is the exclusion of the particular element. Similarly, after this one, I'm just going to, what is the left child? That is inclusion of the second element. What is the second element? That is the A2 element I am just given here. And what is the right child of this one? That is without A2. That is exclusion of that particular element. Without A2 I am just giving here. So likewise we are just going to do this one. So at the last I am just going to get a sum. That is normally called as S. So this S I am just going to compare with the D. So if S is equal to D, what is the concept? That is nothing but it is a solution. We got a particular solution. So we are just reporting that one, that it is an optimal solution, and we are just going to terminate, or we are just going to backtrack and find out the other solutions. If the solution is not found, what we are just going to do here is we are just going to the previous state, that is backtracking to the previous state, and we are just going to find out with other option. That is what's the basic concept we are just going to do with the help of a state space tree. That is given here. If S is not equal to D, what I am just going to do here is that is terminate the node as a non-promising. What is a non-promising node? A node that cannot lead to a valid solution. We are not able to get a valid solution. So I am just terminating the particular solution. Why this termination done? So here we have to go for doing checking with two inequalities. What is the inequality means? I am just going to check S plus AI plus 1. That is the next element in a particular set. If the set that is greater than D, we are not able to find out a solution. That is S is too large. That is not, we are not able to find out a solution. Another one concept, S plus the summation of remaining elements of the set, all the remaining elements of the set, that is again less than D, or automatically we are not able to find out a solution. So that particular node, it is normally called as a non-promising node because it's not able to give a valid solution. So in this state, what I am just going to do is I am just going to backtrack and to find out the other solution. That is normally called as a sum or subset problem. So we are just I am just going to explain this with a particular type, that is the state space tree, that is using a backtracking algorithm. I am just having an instance. The instance that is given as A equal to 3, 5, 6 and 7. What is the target I am just giving here? That is D equal to 15. I am just starting from the initial node. What is the initial node here? 0. What is the weight of this node? That is nothing but it is 0. So what I told that normally it is a we are just considering a state space tree. It is having a left child as well as it is having a right child. What is the left child? It is nothing but inclusion of the first element, and this one is exclusion of the first element. What is the first element? What is the basic thing we have to do is first we have to sort all the numbers in an ascending order. What is the first element I am just taking here is 3 is the first element. I am just including 3. Okay. Next, what is 0 plus 3? That is nothing but it is equal to 3. 0 plus 3, that is nothing but it is equal to 3. That is given here. 0 plus 3. I am just taking here as 3. What is the next element here? 5 is the next element. I am just going to include 5. So with 5, what is 3 plus 5? That is normally equal to 8. 8, that is less than 9 only. So there is a chance of finding again the solution. So I am just going with that one. What is the next one? Here we are just having 8. What is the next element in the list? That is equal to 6. 8 plus 6. What is 8 plus 6? That is nothing but it is equal to 14. So 14, that is greater than which one? That is less than 15. But if 14 plus 7, that is nothing but it is greater than 15. What is 14 plus 7? It is 21. So which is nothing but it is greater than 15. So this is normally a non-promising node, that is a dead end. So I am just going backward. Now I am just going to do again, that is excluding 6. What is excluding 6? See, 8 plus I'm just excluding 6, so I'm just getting the sum as 8 only. Now, in this step, I'm just going to include 7 as well as what is including 7? 8 plus 7. So, what is 8 plus 7? That is normally that is equal to 15. So, this is nothing but a solution because what is the target here? Target is equal to D is equal to 15. So that is nothing but it is a solution. So but here what I am just going to do in the next one, I am just going to exclude this particular 7. Excluding 7, that is 8 only. So any more elements in the set again? No elements in the set. So what is 8? This is again less than 15. So this is dead end. We are not able to explore again. So I am just going backward and going to try with another one solution. What is the solution? I am just going to take with 3. 3 excluding 5. What is excluding 5? Again I am just getting 3 only because I excluded the particular 5. So 3, and what is the next element here? 6 is the next element. 3 plus 6, that is equal to 9. Again 9 plus 7. What is 9 plus 7? That is equal to 16, which is again greater than 15. So this is not a solution. This is a dead end. Again excluding 6. What is excluding 6? That is equal to 3. What is the last element in the set? That is equal to 7. 3 plus 7, 10, which is again less than 15. Again it is a dead end. So I am just again going backward. Okay. Going backward, that is excluding 3 I am just giving here. So this is the normal state space tree what we are just generated in the case of the sum of subset problem. So only one solution here. What is the solution here is I am just going to include 3. I am just included 3. What is the next one? Included 5. And what is the next one? Included 7. So the target that is equal to 15. So this is the solution what I obtained in the case of sum of subset problem. But going to the complexity. So what is the basic concept is the numbers are again and again compared. All the subsets is going to be taken into the consideration. So how many subsets we are able to generate? That is in the range of 2 power n. So the worst case complexity, that is T of n, that is nothing but it is equal to O of 2 of n. So this is a basic concept how backtracking works with respect to the sum of subset problem. In the next application of backtracking, that is nothing but it is a Hamiltonian circuit problem. So main thing I thought that everyone understood the concept of sum of subset problem. Next we are just going to see about Hamiltonian circuit problem. What is Hamiltonian circuit problem is, suppose I am just taking a particular graph. So one graph I am just taking here A, next one B. So I am just going to take a connected graph only. Another one C and next one D. So what is the basic concept of a Hamiltonian circuit problem is we have to visit all the nodes in a particular graph. All the nodes should be traversed. So that is we are just going to create a tour only. But the node should be visited exactly once. The node should be visited exactly once and it should come to the starting node. Okay, that is the starting vertex. So one such Hamiltonian circuit is, I am just going to visit from A to B, then from B to D, it's one possible, then D to E is another one possible, and E to C, that is another one possible, and again to A. So this is nothing but it is a Hamiltonian circuit. So what is here? Here we are having 5 vertices. All the 5 vertices are visited exactly one, and at last we are just reaching the starting node. So this is nothing but it is a Hamiltonian circuit problem. Here also we are just going to use depth first search technique only. So if depth first search technique is optimally, we can going to use the backtracking technique here. So what is the basic concept is we are just starting traversing. What is traversing means visiting the graph starting from the vertex. One start vertex where we are just going to take. So if we are just struck with anyone, that is we are not able to visit the neighbor, or we are just visited already visited node, means that is we are just going to struck with anything. In that situation, what we have to do is we have to go to find out, that is backtrack to other path, that is visiting other unvisited vertex. So that is the basic concept what we are just going to use here. So here also what we are just going to use here is a space tree in order to demonstrate the Hamiltonian circuit problem. So if we reach the starting vertex, means all the vertices are visited equally. So that means we are just getting a Hamiltonian circuit. If not, there is no Hamiltonian cycle. So here one graph I am just giving here is, here we are having totally how many vertices, means 5 vertices here we are having. I am just starting from the vertex number 1. I am just going to take this one as a start vertex. So going to the next slide. So see here, what are the neighbors of the first vertex is, one is the neighbor is 2, another one neighbor is 3, another one neighbor is 5. Okay, that is the neighbor nodes. So here these are the adjacent nodes. 2, 3, another one is 5. So I'm just going to select which one? 2. I'm just selecting the node which is 2. So what are the neighbors of 2? 4 as well as 3. Because 1 is already visited. So I'm just taking 4 as well as 3. I'm just showing this one. I selected 2. What are the neighbor nodes of this one? 4 as well as 5. In this 2, I'm just going to select the node 4. Okay, 4. What are the neighboring vertices of 4? It is 5 as well as 3. So, in this case, I am just going to select 5. What here is, we can go to 1. But if I go to 1 means one more vertex that is left unvisited. Okay, see here. So, here 1, 2, 4, 5, then to 1. This is a cycle. But here, see here, one vertex that is not visited, unvisited. So this is not a Hamiltonian cycle. Okay, may take it into consideration. This is not a Hamiltonian cycle. So what I go to do here is, so the path what I selected from 2 to 4, I am just cancelling out that, because we are just receiving a dead end here. What is the basic concept? A dead end is reached here. So I'm just going to traverse to the previous state. What is the previous node is? 2, I'm just going from 2, I'm just going to visit the node 3. So that is the concept that is shown here. From 2, I'm just going to visit the node 3. Then I'm just going to visit the node 4 that is shown here. Then I'm just going to visit the node that is 5. 5. From 5 we can go to 1. So this is normally a Hamiltonian circuit what we are just getting here. So this is the concept of Hamiltonian circuit problem. So this is the state space tree I am just going to tell here from node 1. I am just visiting 2, 5, 4. I am not getting a solution. So that is we are just getting a dead end. So we are just going to the next one, 2, 3, 4, 5, and I am just getting a solution here, success node here. So this is the basic concept of a Hamiltonian circuit problem. One example that is shown here. So this is an example, that is a sample graph, connected graph I am just giving here. How many vertices here is? I am just having 6 vertices here. A, B, C, D, E as well as F. So I am just starting with an initial node that is called as A. What are the neighboring nodes of A? D, C and B. Initially I am just going from A to B. That is given here. We selected from A to B. From B, what are the neighboring nodes? C as well as F. So here I am just going to select the node that is called as C. C. After that, I am just going to D. Okay. Then to E and then to F. So after F, I'm not able to visit A because in between we are having B, that is an already visited node. What is the rule for a Hamiltonian circuit problem is a node that should be visited exactly once. We are not able to visit twice. So normally this is called as a dead end. So I just going to backtrack here. So from C, I am just going to find out another one route, that is from E to D. I am just going here. But if I just going to D, see here still some more vertices which is unvisited. So what are the vertices it is unvisited is F is not visited. So again this one is considered as a dead end. So simply we are just going to go for the previous state. I am just going to go for F. Here also still some more nodes are unvisited. So this is normally called as a dead end. So from B, I am going to F. Okay. From F, I am just going to E. From E, I am just going to C. From C, I am just going to D. From D to A. So this is nothing but it is a solution. So this is one of the Hamiltonian circuit I am just getting here. So what is a Hamiltonian circuit problem is, so we have to start from a starting vertex. You have to visit all the nodes exactly once. All the nodes should be visited. If one vertex it is not visited means we are getting a cycle, but one vertex it is not visited means it is not a Hamiltonian circuit. You have to visit all the nodes. That is the concept of the Hamiltonian circuit. At the last, we have to reach the starting vertex. So this is the basic pseudocode. What we are just going to have here for the Hamiltonian circuit problem. So in the Hamiltonian circuit problem, I am just going to check the next vertex. So next vertex selection, that is the basic thing what we are just going to take in the case of the Hamiltonian circuit problem. Was net vertex we are just going to select. So if all the vertices are visited, that is k is equal to n, we are just going to print that one as a Hamiltonian circuit problem. Otherwise, we are just going to call this particular one with the next vertex. Okay, that is k plus 1. If k is equal to 1, we are just going to stop. Otherwise, we are just going to the next vertex. How the next vertex is going to be selected, that is the basic target in the case of the particular Hamiltonian circuit problem. One by one, we are just going to check. So main concept is if you are having six vertex should be visited. If one vertex is not visited, that is nothing but it is said to be not a Hamiltonian circuit. Okay, so all the vertices should be visited exactly once and it should give a solution. That is the basic concept of a Hamiltonian circuit problem. Okay, so by this one, so here we are having six vertices. All the vertex combinations, all the permutations we are just going to taken into consider here. Okay, so what is the time complexity is n factorial. In the worst case, what is the time complexity? That is nothing but it is n factorial for a Hamiltonian circuit problem. Okay, so in the previous lecture, we studied about an application for a backtracking problem that is called as Enquiries problem. In this video, we studied two applications, that is one is sum of subset problem and another one is the Hamiltonian circuit problem. So in the next video, I am just going to cover another one new technique, that is problem solving technique. Okay, so we can see. So thank you.